We're going to finish up section 3.2 in this video with a couple of applications of quadratic functions. And here I have a Desmos file open. This one is linked on our resources for the week on our classes page if you want to pull it up for yourself. And I've got a time-lapse picture of a human cannonball being shot out of a cannon. And I also have the equation that best fits the trajectory of this human cannonball. And it's a quadratic function. In fact, all projectiles as they're moving through the air, whether they are rockets or footballs or human cannonballs, generally follow a parabolic path. All right, so we're going to find the vertex of the human cannonball and interpret its meaning in context. So I've copied that formula from the Desmos file for that quadratic function that approximates his path. And I didn't mention it when we were in the file, but those tick marks on the X and Y axis were measured in meters. So we'll keep that in mind when we put units at the end of our problem. All right, so let's find the vertex of this quadratic function. So we know when we're looking for the vertex, the x coordinate, which we used h for, was negative b over 2a. So our b is going to be the coefficient of the x, and the a is going to be the coefficient of the x squared. All right, so my vertex is going to be negative 1.1691 over 2 times negative 0.027. Definitely time for some calculator use here. So let's do negative 1.1691 divided by 2 times negative 0.027. And I get 21.65. So we know our vertex is going to be 21.65 comma something, and we're going to get that something by plugging into the c of x function. All right, so I'm just going to copy my formula down here to figure out my y coordinates. So we're going to plug in negative 0.027 times 21.65 squared plus 1.1691 times 21.65 plus 10.38. All right, so again, rely on the calculator here. So I've got negative 0.027 times 21.65 squared plus 1.1691 times 21.65 plus 10.38. And I get 23.0355, so I'll round that off at 23.04. All right, so this is 23.04. I'm going to sneak back over to Desmos and make sure that that looks like the right coordinates for my vertex. So I got about 21 and change and 23 and change. All right, so we got 21 and change for the x coordinate, 23 and change for the y coordinate, and that does look reasonable based on what we're seeing here. In fact, Desmos will probably give me the answer for this vertex here. 21.65, 23.04 is what I wrote down, so that looks perfect. Let's keep in mind what the x and y coordinates of this vertex mean. So the x coordinate has to do with how far away he is from the cannon. So we're going to say when he's 21.65 meters away from the cannon, then he's at a height of 23.04 meters. Okay, so that's most of the answer here. But because this is the vertex, it's not just about pairing up those numbers, 21.65 and 23.04. That 23.04, because it's the vertex, is the highest that he ever gets. And if he ever wants to move this act indoors, that might be an interesting piece of information to have to make sure that the roof is at least 23.04, probably plus a little buffer, meters tall. So let's just be official and write down our answer here. We're going to say that the maximum height of the human cannonball, we'll call him the HC for short, the maximum height of the human cannonball is 23.04 meters when he is 21.65 meters away from the cannon. That's a horizontal distance. And that mention of a maximum, that's a big chunk of the points whenever I'm grading this problem on the test. Whenever you're finding a vertex and interpreting it, I want you to know, and I want you to point out that you're talking about either the maximum for a downward opening parabola or the minimum for an upward opening parabola. All right, on the last problem, I gave you the formula and we found the vertex. In this problem, we're going to find the function and then find the vertex. So we're going to take this one in a few steps. All right, so this says that traffic authorities have 200 feet of rope to cordon off a rectangular area for parade viewers to stand. So we're going to find a formula for the area of the enclosure when they choose to make it X feet wide. All right, so I'm just going to draw myself a rectangular enclosure. And it doesn't matter if we get the right shape for it, the numbers are going to work themselves out as we go through this problem. All right, so we're going to find a formula for the area when they choose to make it X feet wide. Okay, so we're going to have X feet wide, and that means that this side will also obviously be X feet wide, but then the height of that rectangle will be some other dimension possibly. So we'll call that Y. And then this side would also be Y. All right, so the area of that rectangular enclosure, it's just a rectangle. So we'll just say length times width, X times Y. Right, but we're going to make a slightly better formula for this because we have this extra bit of information. We have 200 feet of rope. Okay, so we can simplify our area equation down to one variable, which is going to be important on the next slide. So I'm going to go ahead and do it here. So we know that we have 200 feet of rope to build that X side, the Y side, another X side, and another Y side. It's perimeter, right? So I'm going to write down that my perimeter formula, 2 X's and 2 Y's, has to be equal to 200. All right. And I'm going to simplify down my area equation into one variable by substituting this perimeter information into my area formula. All right, so I'm going to have 2y. I'm going to subtract 2x from both sides. So I'll get 200 minus 2x. And then I'm going to divide both sides by 2. So I get y is equal to 100 minus x. We divide both of those terms by 2. And that means that I can go replace this y with 100 minus x. Those are the same y's. They're the same height of this rectangle here. So my area equation is equal to x times 100 minus x. So now I have something that is a function. It's a function of x. So all I have to know is x, and then I can tell you what the area of that rectangular enclosure is. I can even simplify this further and distribute that x and make this 100x minus x squared. And I could even use function notation. Now that there's only one variable, we could call this the a of x function. All right, so here is our a of x function. And the next thing they're asking us to do is to find the vertex of it and interpret it in context. All right, so we're going to find our vertex of this function. It might be easier to rewrite it how we're used to looking at quadratic functions with the x squared term first. So negative x squared plus 100x. And there's kind of a phantom plus 0 there at the end. All right, so we're going to find our vertex. H equals negative b over 2a. So my b is equal to 100, and my a is equal to that negative 1 out front. So we're going to say negative 100 divided by 2 times negative 1. So it's going to be negative 100 over negative 2. That's equal to 50. Okay. So my vertex is going to be 50, comma something. To find the y coordinate, as usual, we're going to go plug back into our equation. So we're going to go back to our area function and figure out what is the area coordinate or the y coordinate that belongs to x equals 50. So we've got 100 times 50 minus 50 squared. All right, so 100 times 50 minus 50 squared, and I get 2,500. All right, so what does this vertex tell us? We're supposed to interpret it in context. All right, so we know that that x coordinate is the width of the rectangle. So if I remember my rectangle that I drew here, we found that when we make this 50, then we get an area of 2,500. All right, so we're going to say when the width is 50 feet, whatever our units are. So we're going to say when the width is 50 feet, the area is 2,500. Units are going to be feet squared. And then I'm going to put a comma there. Remember that what I said about finding the vertex of a quadratic function in context. We always need to mention whether this is a maximum or a minimum, because that's what the vertex is. So this area function here is a downward opening parabola. So we know that we're looking at the vertex being a maximum spot. So this is telling us that this is the maximum possible area for this enclosure, is when we make the width 50 feet. Okay, so this is the maximum possible area. So if you want to fit as many people as you can into a rectangular enclosure, which is not something that we have done for about a year, bad for social distancing, but eventually we might want to fit as many people as we can into the enclosure to watch a parade. So if we're trying to fit as many people as possible into this rectangular area, have the most space in there, and we have 200 feet of rope, then we need to make it 50 feet wide. And you may have noticed that this actually causes us to have a square. My picture is not exactly accurate because if I use 50 for this side, I'll have to use another 50 for this side. That leaves me with 100 feet left over to split evenly between the other two sides. Those also have to be 50. In fact, this always happens when you have a fixed perimeter and you're building a rectangle and you want the maximum area, you always build a square. So because the max area of a rectangle always ends up being a square, these problems become a little bit boring and you don't even need to work them out anymore. So how does our calculation change if they create the rectangle next to a building so they only need to build 3 sides out of the rope? Okay, so same situation, except there's this building here. And my enclosure only needs 3 sides to be built using the rope. So we're still going to have a width of X, and we're going to have this height of Y. Right? So our area is still going to be X, Y, but our perimeter equation is going to change because instead of needing to build 2 X's and 2 Y's, I only need 1 X and 2 Y's. So I'm going to have X plus 2Y equals 200. All right, I am still going to solve this for Y so I can replace the Y in the equation. So I'm going to subtract X from both sides. And I get 2Y equals 200 minus X. This is slightly less pretty than the last one. When I divide by 2, I'm still going to get 100, but I'm going to have X over 2 or 1/2 X. And that's what I'm going to plug into my equation. So I'm going to take my 100 minus 1/2 X and plug it in for Y. So my area equation becomes X times Y, which is 100 minus 1/2 X. And then if I distribute my area function this time, so we'll call this A of X, and distribute my X, I get 100 times X minus 1/2 X squared. And again, for finding the vertex, if we want to write that in the other direction, negative 1/2 X squared plus 100X. So then I do my calculation for my vertex. I'm going to say H equals negative B over 2A. My B is still the same thing. I've still got a B of 100, but now my A is equal to negative 1/2. So I get negative 100 over 2 times A. So I get negative 100. 2 times negative 1/2 is going to be negative 1. So I get that my vertex needs to be at X equals 100. All right, and then I can go plug that into my area function. So I'm going to go back up to that A of X and plug in 100. So I'm going to have 100 times 100 minus 1/2 times 100 squared. And we get 5,000. Right, which is much bigger than when we had to build all 4 sides of the rectangle for the enclosure. If we can dedicate that 200 feet of rope to only 3 sides of the rectangle, we actually end up doubling the amount of area that's in the rectangular enclosure.